Welcome everyone. We're just waiting for a few more people to come into the webinar and then we'll get started. Okay, let's go ahead and get started. So welcome everyone. Thank you for joining us for today's webinar. My name is Lori Jerome and I'm the Marketing Manager for Big Sky Insulations and Premier Building Systems. Today we are presenting an engineer's view, building stronger and greener with structural insulated panels, with special guest Brian Von Allwarden, a project engineer from Wright Engineers. In this 1-hour presentation, Brian Von Allwarden of Wright Engineers, along with Premier Building Systems and Big Sky Art Control, discuss the history and options for SIPs from an engineer's perspective. Topics discussed will include why engineers prefer SIPs over stick framing, including speed of construction, the upfront cost savings of labor and materials, the superior structural benefits, energy efficiency of the final, and sustainable benefits over time. Real-life projects and examples will be discussed for both commercial and residential applications by experts from both an engineering and manufacturing perspective. Today's presentation is brought to you by Premier Building Systems and Big Sky Art Control. For over 65 years collectively, Premier Building Systems and Big Sky Art Control have been leading manufacturers of structural insulated panels. Recently, our two companies have combined their technical knowledge and best practices. The brands remain independent of each other, but together, we are the largest SIP manufacturer in North America. The synergies created in uniting Big Sky Art Control's state-of-the-art technology with Premier's most recognized and awarded brand in the business brings the most in-depth technical library and product solutions in the SIP industry to our valued homeowner customers, designers, and builders. So a little housekeeping before we begin. We encourage your questions today and ask that you please type them into the Q&A section of your screen. We will review everyone's questions at the conclusion of the presentation. Our speakers are truly experts on SIP building and construction, and we encourage you to stick around for the Q&A if you have the time. We would really appreciate it as well if you would provide your feedback and share your thoughts with us so we can continually create content that you find informative and educational. A survey will be sent to you after the webinar, along with a recording of today's presentation and the contact information for our speakers. Now, without further delay, I will turn over the presentation to the experts.
Thank you, Lori. My name is Brian Von Allwarden, and I'm a structural engineer with Wright Engineers. Over the last 25 years, my main focus has been on SIPs. And during that time, I've designed, engineered, and built a couple hundred SIP projects, everything from low-cost housing communities to 5-story commercial and residential buildings. And like a lot of you, I'm currently working out of my home, which of course is built out of SIPs. So before we get started, I just want to talk a little bit about what is a SIP. So anybody out there that's not familiar with what they are can understand where we're going. A SIP is a structural insulated panel. And it consists of an exterior sheathing and an interior sheathing, all surrounding an insulated core. Now, today's SIPs, the most common one uses OSB or oriented strand board as the skin on both the inside and the outside. And it uses EPS, which is expanded polystyrene, for the insulating core on the inside. And for the architects out there, it is listed in the CSI division 06-1200. A lot of people think SIPs are new. When you talk about them, they go, well, that's a new product. We don't want to use a new product. But it actually isn't. SIPs started back in 1935 when the U.S. Forest Products Laboratory built what they called a stress skin panel. What they decided was to try to get the forces out of the core of the wall and into the skin of the wall. So a typical 2x construction, all the loads go down through the middle of the wall, through the studs, and not through the skins on the outside. In 1930, they built their first stress skin house using 4x8 sheets of plywood, which were the insulating material within the wall was cardboard. So they built that in 1937. And then in the 30s and 40s, Frank Lloyd Wright got involved, used a lot of SIPs. But in 1952, Dow Chemical came up with an expansion foam, a chemical foam, and that made a difference to SIPs, and that now that became the insulating material between the skins. So that was a big step forward in SIP production. And then in the 60s, EPS came available, and that's a much more stable foam. It's an insulating. It's not quite as insulating as the chemical foam, but it was much more rigid, much more stable than the chemical foam. Between 68 and 84, the biggest SIP user was Woods Construction in Santa Paula. They built dozens of housing communities, residential apartments, commercial buildings, pool houses, things like that in Santa Paula, California. Then in the 80s, the oriented strand board was developed. This was a huge step forward for SIPs. Plywood is typically 4x8 because you can't really make plywood bigger than that because you have to ply off the wood from a tree. Oriented strand board is made from little strands of wood. So you can make basically the panel as big as you can. So it was much larger panels, and it made a huge difference in the SIP world. In 1998, they removed the house that was built in 1937. Up until that time, for the 61 years, 62 years that it was in place, it was used every day. In the end, it was used as a child care center for the University of Madison in Wisconsin. They took it down to actually make more room for the University of Madison in Wisconsin. SIPs appeared in the IRC in 2007, and then in 2013, they became the official ANSI standard. So SIPs can do just about everything that, well, they can do even more than what a stick wall can do. They can support vertical loads, they can support transverse loads, and they can support in-plane loads. The vertical loads are the gravity loads. Those are the loads that are coming down from the floors above, from the weight on the roof. The transverse loads are the wind loads. Those are the winds that are actually hitting the face of the panel, trying to push the panel in. And then there's the in-plane loads. Now, those are the loads that go along the length of the wall. And those are very important because those are the loads that keep the wall from tipping over in high winds or seismic. But SIPs could also do other things. They can provide an exceptional environmental envelope. They can provide straight walls. I don't know if you've ever watched a carpenter build a wall, but a good carpenter will look down the edge of a 2x before standing it up to make sure that the warp in the 2x matches the one he put up before. SIPs also go up extremely fast. It takes about 25% or a quarter of the amount of time to construct a SIP building than it does a stick building. So the thickness of a SIP, the EPS foam core is a dimensional lumber dimension. So that means that that foam core is 3.5, 5.5, 7.25, 9.25, 11.25 inches. That fits dimensional lumber, and we'll see why that's important in a minute. But then they take that foam core and they pressure laminate the oriented strand board. Typically it's 7/16 inch, doesn't have to be. They make 5/8 and 3/4 depending on the use of the panel, but the standard wall panel is a 7/16 OSB. In the other direction, we have standard sizes in the industry. We have 4 and 8 feet in one direction. But in the other direction, they have 8, 9, 10, 12, 14, 16, 18, 20, 22, all the way up to 24 feet. And if you compare that to our little 6-foot guy there, it's a pretty big panel. What's really amazing though, is that that skin on that panel is one piece of OSB. There's no joints in it. It's not like they tried to glue 4x8 pieces together. This is a single solid piece of OSB. So we have our panels. The question is, how do they attach both to the foundation and how do they attach to each other? We'll start with the foundation. Like any other stick building, you've got an anchor bolt. On top of that though, this is where we start changing. We put down a seal or a sealant on the concrete, and then we put a 3/4 inch pressure treated CDX plate. This is called a capillary plate. When concrete is in contact with wood, the water in the concrete weeps out into the wood. So if you put regular non-treated wood on concrete, it will absorb water from the concrete over time. It will start to rot and mold. So you need a capillary break. So any wood that's in touch with concrete or dirt or anything that's moist needs to be pressure treated. The pressure treated keeps the water from migrating in. So this is our capillary break, this 3/4 inch pressure treated CDX. Then on top of that, we put sealant and then a non-pressure treated 2x. That's our sill plate. The reason it's non-pressure treated is that when you put nails in the pressure treated wood, they have to be a special nail. You can't just take any nail off the shelf. You can't use box nails. You can't use just standard galvanized nails. You need a nail that's designed to go into pressure treated wood. Stainless steel or a special galvanized nail. And there's a lot of contractors that don't know that, and they just use regular nails everywhere. The problem with a regular nail in pressure treated lumber is that it will corrode extremely quickly. And then you have nothing holding your building together. So on top of our non-pressure treated sill plate, we'll put a washer and nut, just like you would on any other sill plate. But now here comes the difference. We bring in an inspector. The inspector comes out, scratches his head and says, "What am I here for?" And you have to tell him that you're there to look at the sill plate because tomorrow you won't see it. Because once you put the SIPs in place, it's gone. So he's got to go around, make sure the anchor bolts are in the right place, they're the right size, the right washers. And once he signs off on that, then we can start placing our SIP. So we put our sealant down and then we put the SIP on top of it. It has 1.5 inches of foam removed at the bottom of the SIP and on the sides and on the top, depending on the circumstances of where we're using the SIP. But 1.5 inches of foam down where the sill plate goes is removed. So now the SIP can slide right over that sill plate. The skins fit right next to that 2x because the foam is a 2x dimension distance. And then we simply take and we drive our 1.31 ring shank nails horizontally through the skin into the sill plate. And that's our connection to the foundation. So we have our foundation, we have our first SIP up on our foundation. Now we bring in a second SIP. How do we attach it to the first SIP? Well, there are a few ways. The first way, and probably the best way, most economical way, is what people call a block spline or a box spline or a super spline. It's nothing more than a SIP that is a dimensional lumber dimension. So it's 3.5, 5.5, 7.25 in width, and then it's 3 inches in the other direction. So that 1.5 inches of foam that was removed from the side of the SIP, now this spline fits in there, 1.5 inches on each side. You put sealant in there, you slide it in, and you use your 8-penny nail, ring shank nails to nail it together. One thing you'll notice if you look at the diagram is there's no straight line from the outside of the building to the inside of the building. Any air movement, any movement of the wall has to go around the spline. Now, if we look at a roof or a floor, sometimes there's heavier transverse loads. We want to have a longer span. We want to be able to hold up more snow load or more live load on our floor. To do that, we can use what's called an I-spline. It's like a TJI, and they put foam on either side of the web. And that strengthens the wall in the transverse direction, in the direction pushing against the skin. So now we can make our roof spans longer and save money on our substructure. We can make our floor spans longer or stiffer. So this is another spline that we use typically in a horizontal position, roof or floors. If we have a vertical load, we can use a vertical stronger spline, and that would be a post. So if we have, say, a beam or a girder truss that has 5,000, 6,000 pound point load coming down on the wall, and the wall itself can't take that load, we'll break the SIP at that point and put in a 2 or a 4 by 6 by type member into the wall, and that will take the load from that point load. Now again, if you look at the diagram, there's no straight line through this wall. So we don't take two 2-bys and put them together because they will just pull apart. So we make sure that we do not have a straight line through the wall. When you get to a corner, the panels butt together. One panel pushes in against the other one, and it creates actually a very strong corner. The other thing it does, though, is it provides minimal thermal bridging. As you can see here, that as the panels go together, we screw them together with long SIP screws. The only thermal bridging we have in this corner is 1 2-by. In stick building, the minimum you can have in a corner is 2, and often you have more, up to 5 thermal bridges in a corner when you're stick building. This detail right here can also be used for a roof. So a roof can sit on top of a wall, and then you can screw it together. Very similar detail to this. SIPs save money and time and waste on the construction site by being fabricated in the factory. So when you order a SIP package, you'll get SIPs that arrive on your property that look different. There'll be solid panels, big panels, little panels, fat panels, skinny panels. There'll be panels with windows in it. There'll be panels with doors in it. There'll be smaller panels that you use above and below door openings or window openings. So how does the factory know how to make this? Well, the factory will make shop drawings. This is a shop drawing for Norm's Restaurant in California. And you can see they provide a 3D view that shows every single panel that you're going to be using on that project. They also show elevations of the walls. And every wall has the panels labeled and shown exactly how they go together. They show what kind of connection is used between them. They show where there's posts, where there's in-bucks, that sort of thing. So this is what you use as your guide when you're putting your building together. They do the same thing for the roof, looking down at it, label every single panel. The panels, when they come out from the factory, are also labeled to match the shop drawings. So then it's just like putting together a puzzle with instructions. Here's a little demonstration of how a SIP building could go together. You start in one corner, then you just work your way around. You really don't even need any bracing for the walls. Some walls may have a window in it. There may be a big door where you just put a panel across a gap between panels. Some doors may be built into the walls. You may have big windows where you put a panel at the bottom of the window and another one at the top. So as you come around the building, you finally end up back where you started. And you're done with your walls. They're insulated, they're sheathed, they're tight. The walls are pretty much done. Now this shows a flat top plate. That's not always the case. You could put in a raked top plate, and here I threw a beam in the middle and threw some panels on the roof. Now remember, panels are structural. That's their first letter, structural insulated panels. So they can span quite a ways, and they can cantilever out, and it makes a very simple roof system. One of the things about SIPs is they are a lot stronger than stick building in almost every way. Let's start by talking about gravity. Gravity obviously is the load coming down on the wall, and it can hit the wall in several ways. One is beams or girders, point loads. Well, A SIP can hold a ton of point load, literally a ton, 2,040 pounds. Anywhere on the wall. You don't have to worry about where the studs are or anything, mainly because there aren't any studs. But a stick wall can only hold about 852 pounds. So we can hold about 2.5 times as much point load on a SIP wall than we can on a stick wall. There's also uniform loads. This would be on a first floor where you have walls above it, floor systems, roof systems, all pushing down as a uniform load across the top of the wall. Well, SIPs can hold 4,000 pounds per linear foot. That is quite a lot of load. When we look at our stick building, it can only hold about 2,500 pounds per linear foot. So again, you're looking at about 1.5 times as much load on a SIP than you can on a stick. Headers are the pieces of structural material that go above an opening. So when you have a load in a wall coming down and there's an opening, something has to take that load and move it around the opening. When you do stick building, that can be a number of things. It can be 2 2x6s on end, 2 2x10s on edge. It could be 3 of those. It could be 2 of those in a piece of plywood. It could be a box beam made up of 2 2x going horizontal, 2 going vertical. So there's a whole number of different ways you can build headers in the stick world, which makes it kind of confusing for the carpenter. In the SIP world, there's basically 3 ways of doing a header. The first one is a panel header, which is nothing more than a hole in the wall. So when it comes from the factory, the hole's cut out, 1.5 inches of foam is removed. You simply put 2x material around the hole and you're done. Now about 95% of windows in a residential project are panel headers. Very inexpensive, very easy to build. On a commercial project, anywhere from 40 to 60% are panel headers. So most of the headers are very cheap, very easy, and already cut for you, so they're square and plumb. If that doesn't hold the load that you need, you can go to what's called an insulated header. Now, that is a couple of pieces of LVL that are a certain distance tall. They're 11.25 inches tall. So it's a set piece of material, and it's got foam laminated between it, EPS. And so that is a huge step as far as holding load higher than the panel header. So if your panel header is not strong enough, then you go to an insulated header. Now you can put the insulated header right above the opening if you have a very tall wall, or you can put it at the top of the wall, which makes installation very easy for these type of headers. And again, they are very, very strong. However, there are times they don't work. Primarily, say, on a large garage door that has trusses coming in on it. May not work for that. In that case, you go with a glue lam or an LVL header. 5.5-inch glue lam fits perfectly inside a 6-inch panel. LVLs don't fit quite as well, but you can pad them with plywood. But they will slide right into the panel, just like the other insulated header. And so they're not sticking out, they're not hard to do. When you're putting the panels up, you simply put the panels up and come back later and put the headers in. So you don't have to stop and worry about what kind of header goes in as you're going along putting the panels up. But the glue lam beam can be any height we want. It can be 6 inches, it could be 26 inches. So we can hold just about any amount of load over our opening if we have to, and go to a glue lam or an LVL header. We don't want to because that's a huge thermal bridge, and it does make a huge difference. Staying on gravity, we can look at roofs. Most people say that, you know, a roof panel, depending on its loads, can span about 20 feet. Well, this is my house, and so my roof panel spans 24 feet. But to be economical, you really should try to get your roofs to span 16 to 18 feet. That allows you to use the standard spline in most conditions, and it reduces the amount of substructure you have to hold up your roof. So it reduces the amount of cost in your construction. Now, obviously, if you have heavy snow loads or something, that span will have to come down, or you would have to use I-splines that increase your transverse load capacity. Floors, on the other hand, are typically loaded higher than roofs because you got people walking on them, you got furniture and dogs and all sorts of things. So their spans economically are about 12 feet. So again, it's better than 2 foot on center. You can reduce your substructure by quite a bit by using the strength of the panel to span those gaps rather than having multiple substructure elements. The roofs are also very easy to hold up and attach such things as solar panels, water heaters. Because there's no studs, there's no joists, there's no trusses that you have to try to find when you're putting your connections on. If you're putting a solar panel on, you simply take a flat bottom riser, put it on wherever you want, put in your 9 screws, and you're good as gold. Roofs can also do double cantilevers. And again, most people will tell you you can cantilever maybe 5 feet. If you're in high snow loads, obviously that's less. Well, again, this is the other side of my house. And you can see that I have a cantilever that's 5 feet in one direction, 12 feet in the other. So by using the right engineer, you can push the limits of SIPs and still be very, very safe and conservative. Let's change directions for a minute. Literally change directions. Let's go from vertical to horizontal. Lateral loads are the loads that try to push your house over. One of the main ones is wind. A 10-foot tall, 6-inch SIP wall can withstand 58 pounds per square foot of load against that wall. It will deflect L over 240, but that's acceptable for stucco, not stucco, but it's acceptable for wood siding and that type of siding. But 58 pounds per square foot. How much is 58 pounds per square foot? Well, a hurricane with 200-mile-an-hour winds only produces 52.2 pounds per square foot. So obviously SIPs can withstand hurricanes, they can withstand storms, they can withstand a booze, all sorts of things that you have hitting your house laterally from wind. When you have that wind hitting your house, you have to keep it from falling over, collapsing. And so that's where the shear walls come in. With a SIP, a standard shear wall out of the box, just take a panel, stand it up, nail it off normally. You have 360 pounds per linear foot. With a 2x shear wall, you're only looking at 239 pounds per linear foot. That's your standard basic 2x shear wall. Now, if you double the top plate on a SIP, now SIPs only have a single top plate, but if you double that top plate so you can get more nails in, you can get 1,000 pounds per linear foot. With a 2x wall, you'd have to put 3/4 inch plywood on both sides, 4 bys at the end of the wall, and a lot of nails. And you still only get 920 pounds per linear foot. So a lot more work, less result. The other lateral load is seismic. Now we all know the equation for force. Force equals mass times acceleration, where force is the force that F is the force that the building must resist. So that's the pressure or the force against the building. A is the acceleration, and that comes from the earthquake. So any particular earthquake produces a certain A value, an acceleration value. So the only thing we can change in this equation is the mass of the building. Well, SIPs weigh a lot less than other building materials. They're about half the weight of 2x construction. And they're like 1/15 of the weight of masonry construction. So if you reduce the mass, you reduce the force that the building has to resist, which means you have less weight, less force to resist. 2x construction has more weight and it's not as strong. So SIPs are stronger and have to resist less weight. And stick walls are lighter, but have to resist more force. How do SIPs make a building greener? Well, we're talking environmentally green. And we can do that by the materials that SIPs use. The oriented strand board is made from fast-growing harvest trees. So we have trees that are planted 3 years later, they're cut down and used, replanted, cut down in 3 years. We're not going out in the forest and cutting down old trees. We can also recycle the OSB in several ways. One way we can do it is we can chop it up and use it for livestock bedding. The expanded polystyrene uses steam, not chemicals, to create the foam, to expand it and make the blocks that we use, which means there's no off-gassing from the EPS. And if you burn the EPS, you get carbon monoxide, carbon dioxide, and water. Basically the same things you get from burning wood. Now, obviously, you don't want to breathe in smoke because your body needs oxygen and not smoke to survive, but it's not deadly. And polystyrene can be recycled in all sorts of different ways. They can grind it up and reuse it in other polystyrene materials. The pressure treated wood. We already talked about the fact that we use a 3/4 inch CDX pressure treated. Whereas regular stick construction would use 2x, which are bigger, more chemicals in the material. So that is not as good for the environment. We also don't need to use pressure treated nails, so we can get rid of that requirement. SIPs also use less hardware. So we don't have as many hold downs, we don't have as many hurricane straps, we don't have as many, any of the type hangers, that sort of thing. We don't have as much, which means we're not taking materials from the earth to make the steel, to make the hardware. So again, we're using a lot less, making it greener. We use a lot less nails on SIPs than you do with stick construction as well. The environmental envelope of a SIP house has a true R value of about 23. Now, when I say true R value, if you have BAT 19 in your house on a 2x6 wall, it's not an R19 wall. I mean, you're lucky to get R18 out of it, and that's for a perfectly built wall. And we all know that when you put BAT insulation in a wall, it's not perfect. It's itchy, you don't want to be there, you just kind of stuff it in there. If you use spray foam, you can get 18. Sorry, with BAT insulation, you're only about 15. But with spray foam, you're up to about 18. Now, that's because it goes in, it fills in the cracks and stuff a little better. You don't have air movement through it. But that's about all you get is about 18. And that's for a very good stick-built wall. Standard SIP off the shelf, R23. And here's why. When you have energy approaching your building, it's trying to get through the wall. So it has to go through the EPS. That's the only path it has. And that is very good insulating material. So very little energy gets through. When you have that energy going to a stick wall, it doesn't take the hardest path, it takes the easiest path. And that easiest path is through those 2x. For energy, 2x4s, 2x6s, 2x8s, they are a freeway. So they will just jump over, get on that freeway, and come right into the structure. Infiltration is the second half of your environmental envelope. The first half is the R value, trying to keep energy from coming in or out of your building through the walls. Infiltration is the movement of air. So when you turn on your air conditioner or your furnace and you pressurize your house, all the little holes in stick building, the air just goes right on out. So you're cooling or heating that air, and then you're just pushing it outside. So that is a huge waste of energy. So with SIPs, the building itself is about 15 times tighter than a conventionally framed building, meaning that very little air, actually hardly any air can get out of a SIP building if there were no windows or doors. Most of the air goes out the windows and doors. If you build a SIP building properly, basically no air gets through. So using SIP seal, which is the sealant that we put on between all the sill plates and between the splines we use to put the SIPs together, and using SIP tape, which is a secondary protection on the roof joints and some of the wall joints, we get no air movement pretty much at all. And that saves a tremendous amount on your energy bill. But now let's talk about the other green, money. The problem that you hear from contractors is that SIPs are too expensive. That's because contractors look this far. They look as far as how much it costs to get a stack of SIPs on the project and a stack of 2x on the project. Well, obviously, SIPs have insulation, they have sheathing, they've been fabricated, there's shop drawings. There's a lot that goes into SIPs. So the initial cost of SIPs is higher, quite a bit higher sometimes, than a bundle of 2x4s dropped on the lot. And that's where contractors stop and say, well, it's too expensive. But what they don't look at is what comes next, the installation. Because SIPs go in so much faster, then the labor cost is down and the time cost is down. Then you look at the insulation. Well, there's no cost for the SIPs because it's already there. Sheathing, again, no cost for the SIPs, no time for the SIPs, but there's time and cost that goes into the stick building. Then you look at the hardware. We've already mentioned less hardware, less time, less money. Exterior finish. My stucco guy actually charges less to do a SIP house than he does a stick house. There's a lot of reasons, I won't go into it, but the exterior finishes go on much easier because you don't have to worry about studs. You don't have to worry about crooked walls. Interior finish, same thing. Drywall, you don't have to cut it to find a stud. You don't have to cut that nice factory edge off your drywall. So you get better finishes, easier to install. The HVAC and heating equipment. Now you're talking about smaller equipment, so you have much less cost. General conditions, waste and disposal, toilets, fencing, equipment rental, all that goes down because now you're building your building in 25% the amount of time as it would if you did stick construction. One thing people forget is cost of money. Whether you're borrowing money to build your structure or whether you're using your own money, that money is tied up in that structure. So either you're paying interest or you're not getting interest on that money. So the longer your construction time, the longer your money is tied up, the less money you get. So the cost of money is something you need to think about. Callbacks. SIPs don't rack, they don't move, stucco doesn't crack, nails don't pop, windows don't stick, doors don't stick. So your callbacks go pretty much away. Lost revenue. This doesn't really affect a homeowner so much because they're building it and living in it. But if you're building a structure to rent or sell, lost revenue is the amount of money that you've lost because you're building instead of selling. So if you can build a building in 1 month and sell it, rather than 4 months and sell it, you've got 3 months of that money that you sold. Or if you're renting it, you have 3 months of rent that you wouldn't have if you were building with stick. If you are going to sell the product, you have a higher selling cost because it's a better structure. Energy bills are a lot less. People will walk into it and know just off the bat that it's a better structure because it doesn't move, it doesn't crack, it doesn't make noise. Big windstorms outside, you don't even know they're there. Now, if you look at it, you can see that the cost of SIPs is actually less than the cost of 2x. And if you take off the cost of money and callbacks and just the actual construction, it turns out to be about the same. But here comes the big difference. Your operating costs. Whether you're renting this out or whether you're living in it and paying those bills for yourself, the operating costs of a SIP building are about 1/3 or 1/4 of what they are with a stick building. I live in a SIP house. I have a small solar array on the roof. I don't pay for electricity at all. I pay a $25 grid fee to the electric company because I don't have batteries. So I use the electric company as my batteries. But the solar panels take care of the entire house. And it's a pretty large house with a swimming pool. But there are disadvantages of SIPs. One thing is SIPs burn. So type 1, 2, and 3 buildings, you can't use them in. You can't use them in New York City because they only allow 1 and 2 type buildings. But you can use them in timber framed or wood frame construction, which is typically what most buildings are made of. Miami-Dade, you can't use them there because they don't like OSB. That's just it. They have no real reason why they don't like OSB. They just don't like OSB. So you really can't use it there. If you have a lot of cut up roofs, say you had a lot of valleys or hips or dormers or you had spiral roofs, SIPs aren't the best for that because SIPs need to be supported by something. So your substructure gets more expensive when you have very cut up roofs. You also have a lot of waste in the SIP fabrication process. Pre-planning is required when you're using SIPs. You just can't go out with a bundle of 2x and start building and make changes as you go willy-nilly without any plans. So pre-planning is a requirement for electrical, low voltage, HVAC, headers, doors, that sort of thing. So you need to pre-plan. And some people consider that a disadvantage. Others consider it an advantage. But the biggest one is the contractor's preconceived ideas. They will fight SIPs tooth and nail. You can't blame them because they know how to do what they do, whether they're masons or whether they're carpenters. They know how to bid a job. They know how to make profit on a job. They know how to build one of those jobs. But the fact is, if you bring SIPs up to them, they will argue. They will say, SIPs are too expensive. SIPs, bugs will eat the SIPs. You can't change SIPs in the field. Anything they can come up with, they will use to discredit SIPs. Of course, if you tell them you're going to build a house out of widgets, they'll say widgets are too expensive. You can't change widgets in the field. Bugs will eat widgets. So they will use any argument to stop SIPs, even though they really don't know what SIPs are. So in summary, SIPs can be used both for residential and commercial buildings, anywhere you can use stick, say up to about 5 stories. They're stronger and they're faster to install than conventional framing. They perform better in site and condition. They're to produce, and they're greener to live in because they provide an exceptional environmental envelope. And the overall cost of building a SIP building is less or about the same as a stick building when you put everything that goes into it and look at all the factors. Thank you. Now we're going to turn it over to Phil Ligon to talk about some of the projects that Wright engineers and Premier have worked on. I'm going to start off with Federico's here. This is a little taco shop, and I was talking to the owner when we were starting this project, and we were talking about SIPs, and he's asking how hard they are to put up and work with. And I said, SIPs are so easy. You can take a bunch of engineers out there and build the thing in a day. And he looked at me and said, really? Do it. So I went back to the office, grabbed 4 or 5 of our engineers who have no building experience whatsoever. I mean, they showed up on site with what we call kitchen hammers, little 5-ounce, little nothing hammers, which we just took and threw away. So the 6 of us, we had 2 laborers and a machine operator as well out there. It took us a day to get almost done, and then a few hours the next day to finish up. And these were engineers, and that's all we had out there. We didn't have any carpenters or any, real laborers out there. We had engineers that, have very soft, delicate hands. That's how easy they are and uncomplicated they are to build. Phil, you got some more projects?
Yeah, so thanks, Brian. That was very informative. But now let's look at the projects that all that engineering gets us to. Most people think of SIPs being used for residential construction only, but most people don't realize how much commercial and retail applications there are using SIP construction. SIPs have been used in restaurants such as Benihana's, Starbucks, Fogo de Chão's, Norm's, Del Taco, Bahama Breeze, Federico's, and Walk-On's brands, just to name a few. And including 7-Elevens for the last about 10 years have used SIPs in dozens and dozens of 7-Elevens nationwide. They've also been instrumental in construction of many public and private schools, churches, hotels, apartments, and municipal buildings. A specific project that Wright engineers designed with was Walk-On's restaurant, if you want to advance the slide. And Walk-Ons, we did multiple of these in different locations. This one happens to be in South Texas, but it sped up the construction by 6 weeks, according to the builder, where they would have typically been using stick frame construction. And so they were ahead and realized that extra revenue for 6 weeks because they used SIPs. Brian, what was some of the advantages that, using SIPs afforded you engineering this project?
Well, the architect's concept was to be like a stadium. And you see these big tapered beams here. They go to a tapered beam that goes across the top. So he wanted it to look in that fashion. So instead of using purlins to go between these big beams to hold up some sort of roofing system, we could span that distance with a SIP. So we didn't have extra material underneath ruining his effect of this stadium that he wanted. We still use some steel in the back house, but most of the steel was architectural, and this went up extremely fast, and the owners are very, very happy with it.
That's awesome. The project below is actually a big car wash down in Temecula, California. There's another project that Premier and Wright teamed up on, was Cornerstone. And if you can push play and mute it, this is a little time lapse. What was the process between you and the developer about using SIPs on this project, Brian?
Well, this is a key project in the town of Porterville. It's right on the main corner downtown. So there are a couple of issues that the owner had. The owner wanted to use SIPs because it's a government building and he wanted to keep the operating costs down. But we also used SIPs because to the north, we had a building 8 inches away. So there was no way to get in there and finish off that wall if it was stick. To the west, we had the main street of town, which we could not close off. To the south was another main street that we could close off only temporarily. So we had to start in one corner and work our way out. It also had to be done in a very quick fashion. It's a government job. Which means it's Davis-Bacon wages. So labor was a huge factor. So by using SIPs, we reduced the labor cost tremendously. We got the building up very quickly. We were also able to eliminate a lot of steel and started using the SIPs as the structural element for shear and for gravity. So a lot of the steel inside, the steel columns that were originally they thought they would have to put in, we got rid of.
Can you advance the slide?
Oh, sorry, I wasn't looking at it.
Yeah, next one.
Hold on. Next, there we go.
There you go. So this is some of the construction photos showing how the SIPs were utilized and how we had to actually grow the building from one direction back because of the street that you can see on the front. And then there's some pictures of it closer to finish side. So you mentioned getting rid of a lot of the steel, and steel obviously is a lot more expensive than a wood-based product. The next project that we're going to show you is the Zuni Christian Mission School's gymnasium and sanctuary that we did in Zuni, New Mexico several years ago. And we were sitting down with the builder and the architect, and the steel guy was in the room, and Brian proposed literally cutting all the steel out to save this school that works off donations, and just using wood. And tell us a little bit about this, because the walls are extremely tall. They look taller than the largest panels that are made.
They actually are. The largest panel is 8 by 24 feet. These walls are actually 36 feet tall. So we had to come up with a way of stitching the walls together using basically a running bond system to get the walls to go that high. We also used curved glulam beams for looks. This is a gymnasium, so there's basketball court in there. So these curved glulams are exposed. And then we used the SIPs and just corded them around the glulams. If you look at the second picture up on the, you can see, it's a very beautiful building from inside.
One of the things that was cool about this project, if you look in the lower left hand, the dark brown colored building is an 18,000 square foot school room building that we did out of SIPs several years earlier, and they used SIPs on the gymnasium because of the excellent results that they got with that particular building. And they literally used the same amount of propane on an 18,000 square foot building to heat it during the winter as they did with 2 of their former temp buildings, which were just trailers setting out there in the cold in New Mexico. And there's a couple of pictures of it a little further in, and I think there's one after it's completed. So that's it for me. I'm going to turn it over to Mark Yerbick from Big Sky Air Control, and he'll be discussing a couple of award-winning residential projects that our companies produce panels for. Mark, take it away.
Actually, Mark, I'll take these first 2 since we engineered them. So this first one is the Palo Alto Apartments in Palo Alto, California, which is a high seismic zone. It won the alternative building for the Green Building magazine last year. The whole thing is made out of SIP, roofs, walls. It has an underground parking structure. It has a couple of townhomes, a bunch of apartments, and a penthouse, which is just incredible. It is LEED Platinum, and which was not very hard to achieve when you use SIPs. And this, of course, is built in California, where they have all sorts of environmental rules and regulations you have to follow. And we did all that, and this is what we came up with. This is a 000 home. This was done by an architect. And it is actually a cool house. It's kind of roundish. It's corded, but it's kind of roundish. It has water collection in the basement. It has solar panels. Well, we'll have solar panels on the roof. It is designed, it's right up against that hill. This is a small site. So that mountain behind it's right up next to it. And they use SIPs, and their energy bills are very, very low. Has a HERS rating, you can see 44. It's going to drop to 12 when the panels are on. They did a door test on it, and they got a 1.06 air change, which is less than the 3, which is required by code. So this was also an award-winning building. It got runner-up for high performance. Mark? Mark, you want to take over with the Mariposa Meadows project here? Well, I seem to have lost Mark. Phil, you want to fill in the audience on what's going on with this project?
Sure. Mark, if you get your technical difficulties worked out, hop back in. Green Builder Media, this is a division. Oh, there you are.
Oh, am I back? Okay.
Yeah, you're back.
Somewhere I must have been muted from the panel somewhere. So, okay. Great. Glad to be presenting Mariposa Meadows here. This is actually brought to us by Green Builder magazine, and it's an off-grid project to effect a meaningful positive change for a better world. Green Builder is an advocate for sustainability and provides mind-expanding information that catalyzes and inspires commitment to sustainable living. So, yeah, I'm Mark Yerbick. I've been with Big Sky Installations for about 15 years now, and I work almost exclusively with SIPs. So I'm glad to be presenting with Mariposa Meadows here. The Vision House series is actually a series of projects on a sustainable learning center that's in development stage. And with this, Brian, if you can move forward, what we're looking at is the first builds happened in 2014 with the collaboration of industry professionals who evaluated many system and product assemblies with special attention to the size and impact on the natural inhabitants of the surroundings. So this actually at 10,400 foot elevation, a sustainable project is surrounded by the San Juan Mountains National Forest, and this phase of the project consists of 3 entirely different off-grid structures. Brian? So with this, we're looking at 3 different projects: the Atrium Duet, the Aspen Cabin, and the Studio. And each one of these is a specific design with a small footprint to help the environment in this mountainside that they're on be a sustainable and completely off-grid experience. When we look at thermal specifications of these particular projects, we've actually selected a higher R value and the thicker wall panel for this with the 8 1/4. And this product is actually the Neopore or R Control Max Core GPS product. So it's a graphite infused EPS. What this actually is going to provide us, most people know the difference between EPS and GPS. So the GPS with the graphite expanded polystyrene, these particles in there actually reflect and absorb thermal radiation, and thus improving the ability of EPS to insulate. You actually are increasing the R value by about 20%. So our 4.5 inch thick panel is actually our 8 1/4 thick panel, which has the 7 1/4 core, is an R38 at 40 degrees. And then when we look at the 12 1/4 roof panel on this particular project, it's an R58. So we've got some serious R values with very little thermal bridging. It's a kind of a cross between zone 6 and 7 up in the mountains. It's the San Juans there. Talking about air barriers, Brian went over some of this earlier, but the IACC requirements that air barriers act as air permeability ratings is no greater than 0.004. So what we've done is basically put a test assembly together with our low VOC mastic, which you can see the red dot there. That's air seal product with the SIP tape on the interior or exterior, determined by your climate zone, actually. And so what this does is create a connection or a joint of the panel that has an air leakage less than 0.001, still exceeding today's IECC requirements for air barrier. So it's really big when you look at a SIP panel and air movement through it. Air doesn't move. It's a slow rate of diffusion, if you will. So some fun facts about our project here. You can see first decking down. You see in the second upper right photo, ridge beam and some purlins there. That's actually breaking the span. So at the bottom left, what you see is just a surface spline connection. So there's literally no thermal bridging in this panel with design loads well up over 100 pounds per square foot. Smart to do stickers. You can't see it, but the actual screws are in this panel placed in it on the ground so that once they hit their layout, they're just going to run those screws in and they're good to go for their next panel. Very quick system for roofs. Simple shed coming off the side of it there with a ledger. You can see the beam pockets up here in the gable end, where they're setting, prepping for the roof panels. And as they bring those in and finish it off, they've actually left those pieces of the subfascia out. They'll go back to lap those panel connections together and tie them nice and tightly. So it's a quick system as it progresses. And once crews get rolling, they 2-3 hours on the job start performing GPS core as an overall insulated product for this project. The Mariposa Meadows, they'll be measuring some of the results on lice testing research and performing activities will be highlighted on Mariposa's with a variety of leader events with the goal of educating visitors about advanced sustainable solutions. And please follow Green Builder magazine and anything to do with Mariposa Meadows as they progress. There'll be much more data and information on these buildings to come. The this overall project, Mariposa Meadows, is really brought to us by Green Builder magazine, with a lot of thanks and inspiration. Sarah Gutterman, Ron Jones, and the contributors who assisted in the experience of Mariposa Meadows. I certainly look forward to following this project further as we get data and they continue forward with it. And again, I thank you all for attending, and I thank Green Builders for this opportunity to share. Thanks again.
Lori, I guess we're back to you.
So Phil is going to run through the Q&A questions. Can you see them, Phil? It looks like we have about 10.
Yeah, so the first one was, if you have two framing crews, one who knows SIPs and the other crew to frame inside potentially. Yes and no. Sometimes the same crew that's, you know, your typical framers can be taught very easily. I put SIPs up for 5 years and been with Premier in the manufacturing the last almost 14 years, but I go out to job sites and show framers in 2-3 hours pretty much what they need to know to put up SIPs. So it could be the same crew, but sometimes, yes, we do have a SIP installer come in and then regular framers, you know, finish out the inside. He also asked when truss work's done, bottom core truss is designed to hang drywall on it. How do you do this with SIPs? Well, if you're going to use SIPs as a roof, you typically will eliminate trusses. But if you're using SIPs with the trusses in a hybrid fashion with a conventionally framed roof, then you can go ahead and put your trusses right on top of the SIPs and then sheetrock to the bottom of it. Same way. Radius walls, we can do them. Typically we don't. It is a different process. Big Sky does more radius walls. Premier's presses a little differently. You know, typically that's just a stick framed wall, but they can be done.
Phil, let me interrupt real quick.
Yeah, go ahead.
On a radius wall, depending on the radius, we will cord the wall using SIPs, using 2-foot or 16-inch wide SIPs. Then we would use 1/4-inch plywood on the outside to skin it to give us a nice round curve.
Right. So, and that depends on how tight the radius is as well. So when you handle the depth of the wall when installing windows, Brian, you want to answer that? You've got some 6-inch walls and some 12-inch walls on your house. How did you do that?
Yeah, typically when we do windows, so you could use a brick flange and just drywall in the inside and have a bigger sill on the inside. But typically we use windows without the flange, and we recess them into the wall. So they're flush on the inside, and then they're recessed back to protect the window from the sun. And we have a detail where we use a double like sill plate under the window slope so that we get water drainage off of it. But typically we recess the windows back. Here in Arizona, we've got a bunch of places that require that the front window be recessed at least 6 inches back in the wall, any windows on the front of the house. So we simply 12-inch panels, which are not much more expensive than 6-inch panels, and use those on the front of the house, and then we can test the window.
So next question, are SIPs a completely proprietary product where I'd have to rely on manufacturer literature for design values? Yes, there are code listings for our control. There's code listing for Premier SIPs. Some other manufacturers share a code listing, but you do have to rely on those third-party tested evaluation service code listings, but they're ICC accepted specs. but yeah, that is where you would get that information for each individual manufacturer. Let's see, what is the maximum weight load of a surface mounted component that can be attached to the interior exterior of the SIP wall, cantilevered off? It's really dependent on the screws that are involved and what you're mounting. We do have pull out and shear values for a whole list of different fasteners, screws and nails. So depending on the weight, I have seen someone hang a roll-up garage door off the face of 2 SIP panels. And the only thing that they had in the, as far as regular lumber, was just a single trimmer on either side of the door. So they can take quite a bit of weight, but there are values for that. And you just have to, do the math and make sure that you're using the right fasteners.
Oh, let me interrupt again here.
Go ahead.
There are different ways we attach things both to the ceiling and to the walls. One thing we can do is if we're going to put a bunch of stuff on the wall that hangs out and we need a stronger skin, we could use a 5/8 or 3/4 inch skin. If they're very heavy, we use SIP screws from the inside and attach some sort of ledger or some sort of attachment device on the outside of the wall to attach our heavy structure to. And that's similar to the details we use on ceilings. If we're doing a steel, say, cantilevered veranda or something off of the SIP, we will design it with through bolts that go into the inside of the building. We would then put a steel plate to distribute the load on the inside of the building to help us hold that up. But we have done some pretty heavy objects on the outside of the building. And again, depending on how heavy they are, depends on how we attach them.
Yeah, the Cornerstone project that was in there earlier, we used 12-inch thick SIPs, cantilevering off the roof 52 feet in the air. How far did those cantilever, Brian?
A lot, 4 feet with no backspan. So it was an interesting detail.
So this next one, how would you integrate structural steel for interior elements such as staircases, suspended balconies, and any post-up situation?
I'll take it.
Okay.
Take that one.
Sure.
Go ahead, Mark.
So, yeah, so in this situation where you might have a balcony on a second floor, you might see some cantilevered elements within that deck or what have you, cantilevering out. And essentially those are going to, just like in conventional framing, cantilever back into your floor system with a post. It could even be just a double pack of 2x to post that situation down. Where you have larger loads imposed and you're required to use steel within that SIP panel, we do provide details specific to each job that show the beam size, the pack out of wood that would attach to it, and how that SIP panel actually more or less cripples onto that steel post. So wherever we have staircase headers, ledgers, point loads like that, we're actually splitting the panel at that location and incorporating that detail for the wood post or the steel post.
Cool. Thanks, Mark. You want to grab another one? The price variance between
I think
EPS and GPS?
Oh, sure. Yeah, as I mentioned before, there's about a 10% increase in our value for the product. We're probably running about anywhere from 12 to 15% premium on price, and that depends on a couple of different factors, and some of that may just basically be, design or something. However, and for the most common practical purposes, it's about a probably 12% increase in premium over the standard foam. So we're basically getting an R5 versus out of the GPS core, or the R Control Max versus standard EPS core.
Sure. This next one, interior environment management, post-build, HRV, HVAC, et cetera, requirements. The buildings are incredibly tight, and they're, because of the R value and the tightness of the building, you do necessarily have to reduce your HVAC system because in the early days, people would put, a 5-ton unit on a house that they, would put a 5-ton unit on with a stick frame, and they do that with SIPs, and the units were short cycling and killing themselves. I mean, they literally were just going kaput because they weren't being able to run efficiently because they weren't coming on and being on the length of time that they needed to. So with some actual MEP people and, looking at it from the volume of air and how much loss and how tight they were and how much air they actually needed to push, they actually started reducing the HVAC size. We've done a lot of stuff now that people are just using mini splits. Brian's particular house has a high velocity air system with chillers. He doesn't even have central, well, it's not totally central. It's all different environment zones throughout his house. So you absolutely have to bring in fresh air and reduce the HVAC size. Let's see, it says attaching stucco and thin stone veneers. You've got a solid substrate.
I'll take that.
Go ahead.
Like I said, my stucco guy charges less. Basically, you put your Class D paper on your building, you put your lath on your building, you put your scratch coat on, and that's where it starts. Well, the lath is cheaper because they don't have to find the studs. They can just pow, 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 put it on. The scratch coat, they can press really hard because the SIP is stiff. Even if you have sheathing on 2x, it bends. So they can put the scratch coat on really hard and use less material. And then they put their finish coat on, and it's nice and straight and smooth. They don't have to go back in and try to smooth out their scratch coat. So it's actually less work, takes them less time and less material to put the stucco on. And if you're doing a thin set veneer, it's the same sort of thing. You put your Class D paper on, throw your lath on, your veneer mud on, and then veneer it up. You can also put brick clips. You just screw them into anywhere you need them onto the SIP to help hold your veneer on.
Hey, Brian, could you click in the chat on the YouTube that's got the electrical video since you're still running the screen? Just open up the chat and click that YouTube, and that'll kind of answer some of the questions visually as we're discussing them below here.
Okay.
It says, how do you recommend running the main electrical supply conduit underground feed into the main panel on the external SIP wall? Also, how should the individual circuits be run from the main panel upward? Do you want to take that one?
Sure, I'll take that one. I'll stop looking for the video.
Okay.
There are different ways of doing your electrical. If you have just a few if you're doing an ADU and you have a few circuits, there are vertical chases in the panels already there, and you can make vertical chases easy by just drilling with a paddle bit. So typically what we would do is we would put a surface mounted SES on a system like that, and we'd run our cables, our Romex, and you can run Romex even in commercial buildings inside a SIP. So we'd run our Romex down to our electrical SES, bring it in the back and wire it up. When we get to it's coming in from the top of the wall, we wouldn't have the top plate on. We would then burn a groove in the foam along the top of the wall and run our home runs to where they need to go along the top of the walls. If it's a larger building, we can make a gap in the SIPs. We can leave a 26, 28 inch gap, and you could put a flush mount SES in, and then you can run your home runs directly up through that gap up to the top. If you had trusses, run it through your trusses. However you're going to get your home runs to where they need to go. But you can run them up just like you would a typical 2x framed house. And then when you're done, we just simply put a piece of OSB. It's designed so that the OSB will integrate with the OSB from the SIPs on either side, so we continue our shear. And so you have basically the same situation as a stick built.
The next question, Michael asked, how does SIPs impact a typical inspection cycle? And the great thing is, like on that Federico's, Brian and I were actually going out there a couple days after the shell was put up by Wright's guys, and the inspector was out there, and he's walking around, and we walked over and introduced ourselves to him, and he said, "What am I supposed to be looking at?" He said, I came out here and looked at the sill plate, and basically there's really nothing else for him to look at other than nail patterns and screw patterns, because the insulation and the framing was all done in one step. So he literally was like, well, I guess I don't need to come back until the electrician's done, because there's not a whole lot. So it actually speeds up. Stick framing, there's about 7 steps. SIPs, there's about 3 to get to a framed, cladded, and sheetrocked wall. So there's just way fewer steps, way fewer trades involved, which is, it's time and money. So the next, go ahead.
One more quick comment on that. This is Mark. I think with this respect to, we, in most all jurisdictions, we go through our shop drawing process and engineer review and stamp on that. So we do have special details and considerations called out for the local code official and or inspector to review. So they obviously can't see lumber inside the panel, but top plate, bottom plate, trimmers, but they can certainly see where they're nailed off and inspect it otherwise.
Sure. Do you want to answer David's question about plumbing?
Let's see this. Yeah, in typical cases, when it comes to plumbing, we're looking at okay as penetrations through the panel, running perpendicular to the skins. That's okay. You can actually cut up to a 1-foot opening in the SIP panel pretty much anywhere, as long as you're not affecting a structural member inside of it to utilize for your layout, what have you. So when we're looking at the plumbing systems, if you've got to have it on an exterior wall, for instance, under kitchen sink, lav sink, that may need to be furred out if it's brought from below crawl space area to accommodate.
And the other option of that, Mark, is sometimes we've stopped a panel, put a spline in, started the panel on the other side
Sure.
of the plumbing, and then furred out with OSB, spray foam in that little cavity, and then OSB on the outside, and so now you're back to full coverage as far as you've got minimal thermal bridging in that location.
And that's true. You as long as that top plate runs continuously through your connection, it shouldn't be an issue whatsoever. I've done that for glycol lines coming down off of a roof panel.
And Michael, the next question about electrical, if you can see the videos going right now, that's on our websites as well as YouTube. But the low voltage question, we did a 70,000 square foot school addition in Las Vegas, and they didn't want the low voltage running with the regular electrical because of the interference, I guess. And so we just put another electrical chase in. That Walk-On's restaurant, we put some chases up high because they were doing a lot of televisions over the top of the walls, and that way the chases were there for them. So we can do that custom. This is just our normal switch and outlet heights and vertical about every 4 feet that you see in this video. So we can't put another chase in somewhere if somebody needed it. Let's see, and Eric, the plumbing stacks, we kind of answered that as far as we can do it multiple ways. And the gaps initially, we just cut both sides, have the panel stop and then restart, making that gap. And then we put a spline in both sides and fill it in with, put OSB on one side and then fill it in with foam and OSB on the other side. A practical radius for curved roofs, Mark or Brian?
Sure. Um, you know, what's practical is what works for design, really. So when it comes to a radius roof, we actually can make 14 to 16 foot radius panels on that long axis. So we really, you know, it's more per design. One of the big things with a SIP radius roof is when you're setting it on radius walls and or radius glulam beams, red iron trusses that may be curved 20 foot, 90 foot, whatever. The the great thing with that is that the time to set these panels is exponentially less because you're not cutting in special rafters or purlins to you know, provide the radius you need, plus all the thermal bridging that comes with that. So a practical radius, it's tough. I would say that you know, when we get to a 60 to 70 foot radius, we could probably even look at using a 4 foot wide panel that would lay on there flat and become segmented with the illusion of the radius. And we've done many projects that turned out just beautiful with that
And
as well.
Mark, that's exactly what that Zuni gymnasium was. That
Segmented,
big glue
right.
lens, we just did 4 foot panels. I think they chamfered the bottom edge. There was a tiny gap at the top, so they just filled that in with spray foam after the fact. And it gave the illusion of it being curved, and we didn't have the expense of curving each panel. So
Mm-hmm.
I think that's the last question, unless somebody else wants to
Bill,
throw
I
one in there.
have one I see. I don't know if we covered this one on SIP warranty. I see during installation, what are the common areas that void a SIP warranty? Did we get that question answered?
I do not. I do not.
So, yeah, SIP panel, you know, I'd say one of the main criteria is with a SIP panel, you know, the delamination R value warranty is 20 years pretty much. The R value will never change. It will stay 100% 20-year mark. So I'd be really looking at bearing locations. Are both skins bearing on the deck or to foundation? I would also look at what nail spacing you're doing, whether you have shear walls or not. Things that might void the warranty when it comes to air infiltration is the panel connections or joints not being sealed properly and allowing air through over time. It's kind of tough to hurt a SIP panel, though. They're extremely durable and very, very user-friendly. So I don't see too many concerns on job sites that would affect a SIP warranty.
Yeah, I mean, it's just any other wood product. Don't cover it up wet with a non-breathable membrane. Things of that
Oh, well,
nature.
sure. Common.
Yeah, common sense things.
Yep. Mm-hmm.
And by the way, you know, and we've had people ask this question, and the answer is, you know, it's a better warranty than you're going to get with stick frame construction or regular insulation. The insulation R value has got a warranty. The lamination's got a warranty. The treated for termite resistance has a warranty. So it's better than stick framing because most stick framing has no warranty. And I don't know about the insulation values. One of the other things with a warranty is Premier and Big Sky have been around long enough that if somebody needed to execute a warranty, they could, because both companies have been around for decades. So that's a true plus as well. So is there any other questions that I might have missed? We do appreciate everybody coming today and all the great questions. If you guys have any more questions, reach out to myself, Mark, or Brian, and we'd be happy to discuss anything further with you.
We'll be sending a recording and everyone's contact information to you within 24 hours. Oh, do we have one more question? Looks like,
Oh, did somebody,
so did you answer this one from David Fuller?
which one?
You have 2 framing crews. That looks like the latest.
Yep.
Oh, no, there's another one. Oh, Daniel Fuller.
Yep, we talked about that one.
All right. Oh, it's just Eric saying thank you.
Yeah.
You're welcome,
Thank
Eric.
you, Eric. Appreciate it.
All right. Thank you all.
Thank you.
Thanks, Lori.